Hello friends, welcome back. If you remember, we were discussing about the volumetrics of mix design, and in the last presentation we tried to derive the expression for voids in mineral aggregates based on the fundamental definition with respect to volume. So, we converted or we derived the expression with volume as the parameter to an expression which included measurable parameters or calculated parameters such as specific gravity and weight or percentage of binder. So, we were talking about this particular phase diagram where we have already discussed what are the different components. We have also understood the importance and the meaning of these individual components. So, today we will proceed from where we left in the last class, and we will try to look at other volumetric parameters, we will define it, and then we will try to see the fundamental expression, and then we will try to see how to calculate it based on the values of specific gravity, weights or percentage of different proportions. The next parameter of interest is air voids, and if you try to define air voids, we can say that it just indicates the total air voids that are available in the total mix, which is represented by this vertical arrow, this space which is available. And just like VMA, air void is also expressed as a percentage of total volume of the mix. So, the fundamental definition of air void, where we talk about volumetric expression, is it is the ratio of volume of voids to the total volume into 100. But as by now we have understood that volume cannot be measured in the laboratory, we can only measure specific gravities, we can only measure weight, and we can know percentages of different fraction mostly by weight. So, here the converted expression is this one, where air void is written equal to GMM, which is the theoretical maximum specific gravity, minus GMB divided by GMM into 100, where GMB is the bulk specific gravity of the mix. Now, the question is how do we derive this expression? So, let us start looking at this derivation from the point of view of its fundamental expression, that is starting from the fundamental expression, that is air void is equal to volume of voids by total volume into 100. All right. So, volume of voids can be written as volume of the total mix minus volume of aggregate bulk minus, if you see here, volume of effective bitumen divided by total volume into 100. All right. So, I can write this as Vt, I am just separating it, minus V aggregate bulk plus volume of effective bitumen. I hope you understand this part in the numerator. Let me try to explain you using the phase diagram, that this is the volume we are trying to write. So, I am writing that this volume is equal to this total volume minus this volume, and this volume is equal to the bulk volume plus the volume of the effective bitumen. All right. So, this is this will become 1 minus V aggregate bulk by Vt into 100. So, here now what I will do, I will just try to divide the numerator and denominator here. I will just use the weight of the total mix, and I will divide it in the numerator and the denominator. All right. So, I am just writing it as V aggregate bulk plus V effective bitumen divided by total mix divided by Vt by Wt total mix into 100. All right. So, I hope you can understand that this is nothing, weight of the total mix by volume of the total mix is nothing but 1 by the bulk specific gravity of the mix. All right, because the bulk specific gravity of the mix is equal to weight of the total mix divided by volume of the total mix. And what about this expression? So, if you remember, The theoretical maximum specific gravity GMM is equal to weight of the total mix divided by voidless volume of the mix, is not it? And what does voidless volume include? It includes the volume of the aggregate plus the volume of the bitumen without any air voids. So, this expression which you see in the numerator, the expression which is written, it includes the void of the total mix, which is voids of the total mix minus the air void divided by the weight of the total mix. So, this is nothing but 1 by GMM. This is nothing but 1 by GMM. So, I can write this as 1 by GMM, this is 1 by GMB into 100, alright. So, I am just solving this or rearranging this expression. So, this is GMB by GMM into 100, and finally, we arrive at this expression that this is equal to GMM minus GMB divided by GMM into 100. Okay. So, I hope again this derivation is clear to you, that how we use the definition of the volumetric, the fundamental definition, and then we arrive at the converted expression which includes specific gravity as the parameter. With this expression, I hope it is clear that how we derive for air voids. Before again we see the next parameter air void, let me just tell you few additional things about air voids in a conventional mix design process. So, typically if we look at the mix design, which again we will be discussing about these steps later in this module. So, typically the air void which is taken is on an average 4%. So, we design our mix to have 4% air void content. However, some of the agencies, they also use lower air void or target air void content such as 3.5 or let us say 4%. A thumb rule, because we are dealing with binder content here, and then the air void has to change with the binder content, because our given the solid the volume of the aggregate total aggregate in the mixture is fixed, we can only play with the binder content and change the binder content to change the volume of the effective bitumen if you look at the phase diagram, alright. So, some, as I said, some agency use 4% target air void, some agencies use even lower air voids. Therefore, it is important to understand what is the rate of change of air void with rate of change of binder content on an average. So, the thumb rule here is that with each 1% reduction in air voids, the optimum binder content or the binder content you can say here to achieve this particular level of air void. So, the optimum binder content increases by approximately 0.2 to 0.4%. Now, of course, it is not very easy to just write a statement and believe that it is true until and unless we really fundamentally understand why we say this. So, in order to understand this thumb rule, we can actually try to think about a typical bituminous mixture. So, let us say we have a typical bituminous mixture and we are talking approximately here. So, if I assume that this is an absolute cylindrical volume, then the volume will be pi r square h without any surface deformations, alright. So, I am assuming that it is a smooth surface. So, the volume exactly is equal to pi r square h. So, for a normal Marshall sample, let us say if you look at the Marshall mix design, of course, we have not discussed about the details, but I am just trying to explain it from some perspective to just understand about this statement. So, in a normal Marshall sample, the dia is equal to 101.6 mm and the height is equal to approximately 63.5 mm, the standard height of the sample. So, the volume becomes equal to pi into r square. So, 101.6 divided by 2. So, 101.6 is the dia into 63.5. Alright. So, this is this, if you solve this, this will come equal to 5147 17.68 mm cube. alright. So, this is what you will get using a calculator. So, now I am saying that each 1% reduction in air voids. So, if by volume, what is that 1% by volume of this total volume, because this is a total bulk volume and air void is a part of this bulk volume. So, if I am trying to look at 1% volume in this mixture, so this 1% volume becomes equal to how much? 5147.1768 mm cube, alright. So, this is the volume, 1% volume of the total mix. Now, the question is how much binder will be required to occupy or to fill this volume, alright. So, let us say that the specific gravity of the bitumen is 1.02. So, I am trying to calculate what is the weight required to fill this volume. So, I am looking at this volume. So, this is in centimeter cube, this is equal to 5.14717768, because this is expressed as grams per centimeter cube. Okay. So, the weight if you calculate it will be approximately equal to 5.2 grams. Now, which means 5.2 gram binder will be required to occupy this volume, alright. Say I am making this bituminous mixture using 1200 gram aggregates and plus the binder content, alright. So, let us say the first trial was 5% or 4.5%, any percentage, and our calculation told that 63 gram is required for some x percent optimum binder content, alright. So, this becomes equal to how much? 1263 grams total weight of the mix. Okay. So, this 63 grams for this 1263 grams into 100 if you do, this is equal to 4.98%. So, which means that the binder content is 4.98% here, and I am saying that if I add 5 gram more to this mixture, then it will occupy 1% additional volume. So, if I am just trying to add 5 gram extra to this 63 gram, which means it becomes equal to 68.2 grams now. I increase the binder content by 5.2 grams, it becomes 68.2 grams. So, if it is 68.2 grams, my aggregate is 1200 gram anyway. So, the total weight of the mixture becomes equal to 1268.2 grams. If you do the calculation in percentage, so this is 68.2 divided by 1268.2, this will be approximately equal to 5.3%, which means this is the binder content. So, how much increase in binder content we have seen? So, you have to compare these two numbers. I am just using a different color here to explain. So, you have to see what is the difference in these two. So, 5.30 minus 4.98 is equal to almost 0.3 percentage. So, therefore, the statement, the thumb rule is approximately correct that 1% reduction in air void, which we have done by adding 5 gram 5.2 gram binder, approximately increases the optimum binder content. So, now the optimum binder content is 5.3%, earlier it was 4.9%, in the range of 0.2 to 0.4%. So, this range we are getting as correct. So, again this will depend of course on the type of mix, shape of the aggregates and so many other things, but and compaction level, but right now we are just looking at an approximate expression. So, I hope this is correct when I say about the relationship between air voids and the binder content. With this, let us move to the next parameter, which is voids filled with bitumen. Now, essentially as the name suggests, this indicates how much space in the voids and what is the total actual void. This is the total void, out of which this is the void filled with bitumen and this is the air void which is left. So, how much space in the voids available, which is VMA, is filled with bitumen. So, I am trying to look at this particular, the one which is now highlighted using a red arrow. I am trying to look at this volume, alright, the volume of the effective bitumen. So, again the fundamental expression, if you see with respect to volume, it is the volume of effective bitumen divided by the total space available, which is volume of voids plus volume of effective bitumen multiplied by 100. Okay. So, again I hope that this is clear to you. Look at this expression and then try to derive the converted expression in terms of already calculated parameters or measurable parameters. So, if you see the formula for VFB, it includes VMA and air voids, and we already have an expression for VMA and air voids. So, if we can convert VFB in terms of VMA and air voids, we can actually do the calculation based on various specific gravities, weights and percentages. Here also we will try to derive this before we move forward. So, this derivation is in fact a little simple, because I will tell you how. So, this is what you are looking at. So, the numerator here, so I am just writing here at the top. So, the numerator I am writing is VEB plus VV, and I am also subtracting a VV here, and then in the denominator I have VV plus VEB, alright, into 100. So, I am just rearranging this and then adding and subtracting the same thing in the numerator. So, if I separate this by part, I will have 1, I am taking this out here, 1 minus VV by VV plus VEB into 100. Okay. So, if you see it here, and now what I am trying to do, I am trying to divide the numerator and the denominator by Vt. So, Vv plus Veb divided by Vt into 100. So, what is written here? V volume of voids by total volume is nothing but air voids. Volume of void plus volume of effective bitumen by total volume is nothing but equal to VMA into 100. So, this brings us to our final converted expression. This is VMA minus air void divided by VMA into 100. So, I hope again this is pretty much clear to all of you. So, now we will summarizing about the volumetrics, we will discuss the importance of each of the volumetric parameters, but let us move forward, let us try to see other parameters and how to derive them and what is the associated formula for calculation of these parameters. So, now we come to the most important expression for which we are actually doing so much of calculations previously, because I already told you that GSE is the effective specific gravity of the aggregates. So, this is an aggregate property and not a mixed property, but since it cannot be measured in the laboratory unlike GSB or apparent specific gravity, we are trying to calculate it using volumetric parameters. So, if you see the expression, the formula is GSE is equal to 1 minus PB, which is the percentage of bitumen, divided by 1 by GMM minus PB by GB. Now, this is very interesting here, because I am saying that this is an aggregate property, does not depend on the property of the mix, but here the formula says that it is a function of GMM, which is in fact a function of the mix. So, this appears to be a little confusing at first, but I will tell you in some time that using this expression, I mean by using this expression, how do we still say that GSE is a property of the aggregate and is not dependent on the actual property of the mixtures. So, before that, let us first write GSE in terms of volumetric parameters and or in terms of volume, and then we will first derive that how using the volume we come to this particular expression. So, this is very important and I would like you to understand it properly or try to agree upon this derivation which we will be discussing, because this is one of the very critical and important parameter in the mixed design process. So, GSE we were saying this is equal to weight of the aggregates divided by bulk volume of the aggregate minus volume of the aggregate not filled with bitumen. Okay. So, this is the actual verbal definition of effective specific gravity of the aggregate. This is the weight of the aggregate and the volume is equal to the bulk volume minus the volume not filled with bitumen. So, I will just again draw a picture which we have already discussed several times during our discussion. So, these are the, let us say, the water permeable voids, but we understand by now that if bitumen is coated over this, the entire void will not be filled with bitumen. So, I am trying to look at the solid volume here. I will try to use a different color again. I am trying to look at the solid volume, all right, the solid volume, this part and this part. Okay, so, this is the volume I am interested in. So, now how do I write it in reference to this particular phase diagram? So, this is equal to weight of the aggregate divided by, the denominator becomes very important, and I will request you to pay a little attention when I am referring to the phase diagram here. So, you see this says bulk volume minus volume of aggregate not filled with bitumen. So, I am basically what I am saying, I want this volume minus volume of bitumen, volume of aggregate not filled with bitumen. So, I am trying to find out this volume, all right. But if you see the vertical arrows here, I do not have any specific definition of volume for this particular arrow here. So, then how do I write it with respect to the phase diagram? So, I will try to write it in this way, that this volume, the one in red arrow here, this one is equal to the bulk volume of the aggregate plus the effective volume of the bitumen, all right, minus this total volume of the bitumen. And these three arrows I have specific volumetric definition, and I hope you see, if you take this entire volume and subtract this particular volume, you get this volume which is of my interest, is not it? And this is what I am doing. I am first writing this. So, this is 1, this is 2, this is 3. So, 1 plus 2 minus 3 will give me this volume, if you try to see it very closely, and this is the most critical part to understand here. So, I am just writing it the same thing here, assuming that you have understood it by now. So, I am writing it, this is equal to V of aggregate bulk plus volume of effective bitumen minus volume of bitumen. Okay. So, this is what I have written here, and I hope that this is pretty much clear by now. So, what I will do here now, I am writing it in this way, that this is weight of aggregate divided by, I am separating this. So, this I am writing it as volume of, I am just writing the same thing, but I am adding one bracket here, all right. Now, you see, if you see this volume is volume of aggregate bulk plus volume of effective bitumen. If you remember, this volume pertains to the expression of theoretical maximum specific gravity, where we said that GMM is equal to weight of the total mix divided by the voidless volume of the mix, which is nothing but equal to V of aggregate bulk plus V of effective bitumen, all right. So, this becomes equal to weight of aggregate, volume of aggregate plus volume of effective bitumen. From this expression I can write it as weight of the total mix divided by GMM. Volume of bitumen I can write as weight of bitumen divided by specific gravity of bitumen. So, GB, specific gravity of bitumen. Weight of aggregate, I am just writing it as it is right for now. So, this is WT divided by GMM. Weight of bitumen I am writing as percentage of bitumen into weight of total mix, because we know that the percentage of bitumen is defined with respect to the weight of the total mix. So, this is divided by GB. Okay. Now the denominator W aggregate I can write as weight of total mix minus weight of bitumen, is not it. So, this is I am writing as weight of bitumen, and this I am writing as Wt by Gmm minus Pb into Wt divided by Gb, alright. The numerator, now if you look at the numerator, again I can write this as the Pb into Wt, weight of bitumen, divided by Wt by Gmm minus Pb into Wt by Gb. So, now if you see Wt is common in the numerator as well as in the denominator. So, I am just removing it. So, this becomes equal to 1 minus Pb, this becomes equal to 1 by Gmm minus Pb by Gb, and this is what you see is the derived expression. So, again I hope that this is pretty much clear to you, that how we calculate the effective specific gravity based on the other volumetric parameters. Now, let us come to our confusion here, that on one hand we are saying that the effective specific gravity is a property of the aggregate and should not depend on the mixture property, but in the expression we have parameters that are related to the mixture properties. So, to understand this you have to understand that, let us say we are preparing several samples, alright. So, first of all let us understand that why do we call this as the aggregate property, because for a given source of binder and given source of aggregate, irrespective of the bitumen content, alright, irrespective of the bitumen content, the amount of binder or amount of that particular binder which we are using for the construction, this aggregate will absorb will remain constant, because absorption is the property of the aggregate, alright, for a given single binder source and single aggregate source. Let us say we are preparing the sample at 5% binder content. So, what we will do here, that for 5% binder content, the mixture which we get, alright, this mixture, for this mixture we will do the GMM test, which is basically the theoretical maximum specific gravity, and we have already discussed the laboratory test procedure to conduct or to complete this test. So, we will do the theoretical maximum specific gravity test and we will determine the GMM at 5% binder content. Now, once we have the GMM at any binder content, we will put this expression here, alright. We know that we have used 5% binder content, we also know the specific gravity of the bitumen which we have used, you calculate GSE. Okay. Now, GSE by this calculation will become constant. Now, for this mixture, irrespective of any other binder content, maybe you are making the mixture at 4% binder content, 4.5% binder content, 5.5% binder content, any binder content, the amount of absorption which will take place will be same and only the value of GMM will change. So, what we do typically, that for any one particular binder content we will measure the GMM in the lab, which means we need not measure the GMM again and again at different binder content to calculate air voids or any other volumetric parameters. So, you will do the measurement only once, from this measurement you will find out GSE, which will remain constant for this aggregate source and binder source, and at any other binder content, because at any other PB, alright, we will calculate GMM, we will not measure it again. So, this is another use of GSE, that once you get the GSE with one single GMM, you can calculate GMM at any given binder content, because the GSE will become fixed, alright. So, I hope this is clear to you. We will now move to the next expression, which is PBA. Okay. So, PBA is the percentage absorbed bitumen. Okay. So, this is the one which we are talking about, and PBA, unlike PB, now this is also one important point here, percentage absorbed bitumen is expressed with respect to the weight of the aggregates, because this is an aggregate property, again not a mix property specifically. So, percentage absorbed bitumen is expressed as by weight of the aggregates and not by the weight of the mixture. So, PB is equal to weight of bitumen divided by total weight of the mix into 100, whereas PBA is equal to weight of the absorbed bitumen divided by weight of the aggregates into 100. This is the difference. Therefore, again one important point to note here is that PBA plus PBE is not equal to PB, because PBE maybe we are expressing with respect to the weight of the total mixture, PBA we are expressing with respect to the aggregates. So, this does not give us the total percentage of binder which we are using, alright. So, again this is something which is very important to note in the mixed design process. Anyways, so our definition of PBA as we have defined it, this is the weight of the absorbed bitumen divided by the weight of the aggregate multiplied by 100. Okay. And weight of the absorbed bitumen, I do not have a direct process to measure this weight. So, ultimately I will have to take the help of specific gravities which I have measured or I have already calculated to finally calculate the percentage of absorbed bitumen. Okay. And you try to understand that these many calculations which we have discussed, the derivation of VMA, the derivation of air voids, the derivation of GSE, all this has been done finally to calculate the percentage absorbed bitumen which we cannot measure in the laboratory. If we can develop tomorrow a procedure to measure accurately the percentage of absorbed bitumen or the bitumen absorption by the aggregate in the laboratory, the mixed design calculations or derivations or measurements which we have been doing, it will not be required, and the steps of the mixed design process, especially the volumetric steps or calculations in the mixed design process, will become very simple and easy for us. However, in the absence of these procedures, we are doing all these calculations and derivations finally to arrive or to calculate that how much binder will be absorbed in the given source of aggregate, alright. So, finally we have to convert this expression to this expression. So, let us see the derivation. So, here what I am doing now, weight of absorbed bitumen I can write as specific because G is equal to W by V, alright. So, W becomes equal to G of bitumen into volume of absorbed bitumen divided by, this is weight of aggregate. So, this is becomes equal to GSB into volume of aggregate bulk into 100. Okay. So, what I am doing here now is that I am adding and subtracting GB into volume of aggregate bulk minus GB into volume of aggregate bulk divided by GSB into volume of aggregate bulk. So, I am just adding and subtracting using this. So, now what I will do, I am taking this expression and this expression, I am combining this expression and this expression, and the middle one I am keeping it separate now. So, this becomes equal to GB into volume of aggregate bulk minus GB into volume of aggregate bulk minus volume of absorbed bitumen, okay, divided by GSB into volume of aggregate bulk. Just for my convenience I have done this. Now what I will do, that in the numerator and in the denominator I will divide by the weight of the aggregates, alright. I will divide the numerator and the denominator by weight of the aggregate. So, this becomes equal to GB into volume of aggregate bulk minus GB into volume of aggregate bulk minus volume of absorbed bitumen divided by weight of aggregate whole divided by GSB into volume of aggregate bulk divided by weight of aggregate. So, do not get confused that in the derivation V of A bulk is actually equal to V of AGG bulk. So, sometimes I just wrote it V of A bulk and sometimes I wrote it as V of AGG bulk, and VAB is actually absorbed bitumen. Sometimes it is confusing. Alright, so now I am just trying to rearrange this expression here. So, just again to inform you that V of aggregate bulk divided by W of aggregate is equal to 1 by GSB, is not it? This is obvious, by now we know this. So, this is equal to 1 by GSB. So, therefore, I am just first in the numerator I will separate the expression. So, this becomes, maybe I will write it here, due to lack of space I am just removing this arrow using a different color. So, this is equal to GB into V of aggregate bulk divided by W of aggregate minus GB into volume of aggregate bulk minus volume of absorbed bitumen divided by W of aggregate divided by GSB into volume of aggregate bulk divided by weight of aggregate. Alright. So, now what we have, this V of aggregate bulk by W of aggregate is equal to GSB. So, this is GB divided by GSB minus, try to understand this expression. This is like inverse of weight of aggregate bulk by volume of aggregate bulk minus volume of absorbed bitumen. So, I think from our previous discussion we know that if we subtract this volume by this volume, this gives us the volume corresponding to the expression of GSE. So, weight of aggregate by this volume is nothing but equal to GSE, which means the expression in the numerator becomes equal to 1 by GSE. So, this is equal to GB into 1 by or GB by GSE, alright, divided by GSB divided by GSB. Okay, so, GSB, because V of aggregate bulk by W of aggregate bulk is equal to GSB. So, this just gets cancelled. So, now what we have here, we will just take out a GB outside, which is common, and we have 1 by GSB minus 1 by GSE, and this is nothing but this expression multiplied by 100, which was always there outside the bracket. So, you know, I again hope that this derivation is clear, and I will recommend that you remember or practice or understand this derivation, because then only you will be able to connect yourself to the volumetrics in the mix design process, the volumetrics of the bituminous mixtures, and you will feel more confident when you are executing any or solving any problem related to the mix design of bituminous mixtures. You will never get stuck in the process if you understand these derivations, if you understand the phase diagram. As I was mentioning that most of the efforts which we are doing in the mix design in these calculations, understanding this derivation, is for finding out the effective specific gravity of the aggregate, because ultimately we are interested to know the absorption of bitumen in the aggregate, and if, as I mentioned, we can someday find a process of measuring the bitumen absorption using some method, the mix design process related to the volumetrics can be completed in just a few simple steps. Some of the researchers, they have also tried to correlate the absorption of bitumen with the water absorption, because if, as I told you, if this is the void which can be completely filled with water, and then we are talking that if the bitumen will come, which is more viscous, this void will not be completely filled with water, but partly will be filled with water. So, researchers have an explanation that bitumen absorption is nothing but a proportion of water absorption, and water absorption is relatively more easier to measure in the lab because we can have a saturated surface dry specimen here. So, a thumb rule which have been sometimes used, sometimes argued is that the bitumen absorption ranges from approximately 50 to 70% of water absorption. So, in absence of any equipment for measurement, or if there is some repeatability issues in the measurement, or if you want to just have an approximate idea about the volumetrics of the source of the mixture prepared using a specific source, you just measure the water absorption. A thumb rule of 50 to 70% of the water absorption can be taken as PBA, and once you have PBA, you can actually calculate everything in the mixed design calculations, and you will have the calculation of air void will also become very simple for you. You need not spend much time in measuring the parameters in the lab, but however, just a word of caution that this is just an approximate idea, not an absolute idea of what will happen in the actual case when you are working in the laboratory. Okay, so now let us discuss about one last volumetric parameter which is also very critical and related to the performance of the bituminous mixture, and that is dust to binder ratio. Okay. So, dust to binder ratio, or we also call it as filler to binder ratio, is defined as the ratio of the percentage of aggregate passing the 75 micron sieve, because this is the one which we call as filler, 75 micron sieve, to the effective binder content. I am sorry for this spelling mistake here. So, this is effective binder content, alright. And again, sometimes students are confused that filler to binder ratio is actually equal to the weight of the filler by weight of the weight of the bitumen, but it is not actually the weight of the bitumen, it is the weight of the effective bitumen, and it is very obvious because the other part of bitumen is inside the bulk of the aggregate, which is not active, which is not interacting specifically with the fillers. So, we always have to consider the effective bitumen when we talk about the dust to binder or the filler to binder ratio. So, the definition will just repeat that this is the ratio of the percentage of aggregate passing 75 micron sieve to the effective binder content. Typical allowable range is 0.6 to 1.2, and this has been decided based on studies on various mixtures, based on experience and a lot of research work. So, and again some of the researchers also suggest that instead of using the filler to binder ratio of percentage by weight, it is better to use it as by percentage of volume, because different fillers can have different specific gravities. So, for the same weight the volume will change, and therefore, they think that since it is an important parameter related to the performance, specifically fatigue response of the mixtures, and also related to other parameters, for example workability, for example stiffness of the mixture, it is better to describe it by volume. But the present specifications which we have, it describes dust to binder ratio as ratio by percentage of weight of aggregate passing 75 micron sieve and the percentage of effective bitumen. So, as I was mentioning, the typical allowable range is 0.6 to 1.2, and as per MS2 of Asphalt Institute, there are some exceptions if we have aggregate gradation with smaller nominal maximum aggregate size. For example, if we have aggregates with 4.75 nominal maximum aggregate size, the suggested range is 0.9 to 2, whereas for coarse graded mixtures, so these are mixtures which are below the maximum density line, is 0.8 to 1.6, and as I was mentioning that this is a critical parameter and it describes the workability in the mixture, and if you have too low filler to binder ratio, it can produce tender mixes which are difficult to compact under rollers. If you have very high, again you will have a tender mix which will be difficult to compact under the rollers. Typically with increase in the amount of filler to binder, increase in this ratio, the stiffness increases because the amount of dust is increasing, which has very small surface area. So, it acts as and it goes inside the existing voids of the mixture, can improve the interlocking properties. So, the stiffness of the mixture increases, and it also controls the workability characteristics as I have already described. It also controls the requirement of binder for a fixed air void content, which is very obvious because with increase in surface area more binder will be required, considering we have a fixed criteria for air void. So, more binder will be required to coat this surface, and therefore, the amount of or the optimum binder content will increase. Well, with this I think we have discussed most of the volumetric parameters, we have tried to understand them, and with this knowledge we should be almost ready to undertake the mixed design process, which we will be discussing subsequently. But before that we also will understand probably in the next presentation about the importance of at least 3 critical volumetric parameters, that is voids in mineral aggregates, air voids and voids filled with bitumen, the importance of these parameters. Some of the concluding remarks related to the volumetrics and the mixed design is that the normal mixed design does not incorporate direct measurement of performance. Now, this is an early statement right now, but I wanted to make this statement at this point, so that when we are done with the mixed design process, we can actually accept this statement and we can understand that what are the aspects missing in the present guidelines which needs more attention, which needs more research in the future. So, the normal mixed design process, it does not incorporate direct measurement of performance. So, historically we have always used volumetric parameters as indicators of performance. So, engineering or the science in materials related to bituminous mixtures have taken a leap in the recent past, you can say, and there are so many materials, so many binders which have come up, and then when this was believed that only volumetric parameters are indicators of performance, is typically not accepted in the present times, when we have so many materials of different varieties with different with individual mechanisms of the response to any given loading condition. So, only volumetric parameters are not found to be very good indicators when these materials are used, but conventionally if we have unmodified bitumen and normal bituminous mixture, then of course volumetric parameters have been related to the performance of the bituminous mixtures. So, ultimately the idea in the mixed design process is that we have to produce a mix, and this the same statement I will repeat at the end of our discussion in the next presentation, that the idea is to produce a mix. And how do I produce a mix? By selection of an aggregate gradation, which again just to recall that we are doing it empirically based on the maximum density line. So, we have to select an appropriate aggregate gradation and an appropriate binder content, so that we meet some of the requirements of the volumetrics. Now, this mix which we will produce, when it will be subjected to years of traffic, should produce a mix with 4% air void. So, this will be our mix design criteria, that in the laboratory we are giving a compaction level which is actually representing the actual compaction after years of traffic, and when this entire traffic will or this traffic will move on my mixture with a given design life, the final air void at which it should compact should be 4% or should be in a range with an average of 4%, so that we have certain level of air voids present in the mix. And how do we do that? We do that by selection of an aggregate gradation and binder content, alright, based on the anticipated traffic. And here again is one more critical point, that the compaction level which we are giving in the laboratory, we will again talk in detail when we discuss about the steps of mixed design, but this is just to ponder upon, food for thought, that all these things will change when we talk about volumetrics. Volumetrics is dependent on the compaction level. Compaction level is dependent on the anticipated traffic. Anticipated traffic is random, because for different locations, for different traffic conditions, the anticipated traffic changes. But the question is, for different anticipated traffic, do we use the same compaction level in the laboratory? If we are using the same compaction level in the laboratory, does this really hold true when we say that ultimately after years of traffic it should arrive at 4% air void? Why do we say that? So, the idea is to use or select an aggregate gradation and binder content based on the anticipated traffic, and the compaction level in the laboratory which we have to use should also be chosen according to the anticipated traffic. So, we will see that how do we incorporate these aspects in the mixed design process which we will be discussing. With this we will end here today, and we will meet again in the next lecture, where we will discuss about the importance of 3 volumetric parameters, including voids in mineral aggregates, air voids and voids filled with bitumen, and also we will solve a problem incorporating entire knowledge which we have gained till now related to the volumetrics. Thank you.